Hello, good morning, good evening, good afternoon, everybody, wherever you might be. Today it's my great pleasure to introduce RYSZARD from Copenhagen, and he will report on his joint work in progress with Elmar Schroer. And it is about the boundaries of pseudo-referential operators and automorphisms of Boutet de Monvel Algebra. It's all yours. Take it away.
Thank you. So thank you for invitation and Happy New Year, everybody. And as said, this is, well, it is a work in progress. Basically, we have to find time to get together and finish writing it up.
Absolutely.
But it's still with problems. Yeah, that's the problem of getting together somehow. I'm not really good at working online with people. But anyway, so boundaries of the operators and automorphisms of Boutet de Monvel algebra. So you had Elmar's talk, I think, 2 years ago, a year ago and a half ago, about Shubin type, similar question for Shubin type operators. Now this part, this is with boundaries, so operators on manifolds with boundaries. And let me just start by saying something about boundaries. So how do I understand dealing with boundaries? Down. So before we deal with boundaries, so let's think about boundaryless case. So M is just a smooth manifold without boundary. X is vector field. Let's say M is compact. Or well, M is complete. Then given that such a vector field, there's always a one parameter group of diffeomorphisms of X. So automatically you get that. So X gets a set of analytic vectors. And actually, they are all joint analytic vectors for all vector fields X. So since we have this dense set of analytic vectors, X has unique extension such that minus IX is self-adjoint. So, so T is just the extension. So automatically to any X, you can associate the corresponding self-adjoint operator IX. So I wrote T here. And now you have now you can work with these operators. So you have this algebra of these operators with the same family, the same space of analytic vectors. So calculus with these operators and their products and such is purely algebraic. Since we have joint the domain of analytic vectors, there are no problems adding those unbounded operators or anything like this. So this is the background for pseudo-shell operators. That's why pseudo-shell operators are so useful in computations. So, oops, sorry. No. 1, 2, 3, yeah. So before I get to pseudo-differential operators, let's just think about something about differential operators. So they have this degree filtration. So everybody knows that the operator has a degree. And this degree filtration has these properties that's a filtration. So product operator degree n and m has degree n plus m at most. And the commutator operator of degree n and m has degree n plus m minus 1. So this means that if we can look at the associated graded algebra, so direct sum of quotients dn plus minus 1 over dn, and this is the fact that this filtered algebra, we get the conclusion that this graded algebra is commutative. Well, commutative algebras are typically functions on some space, and in this case, we are just polynomial functions on the cotangent bundle, which are so smooth fiberwise polynomial. And the quotient map from dn to dn of modulo dn minus 1 has as the image is isomorphic to polynomials of degree n on the cotangent bundle. So given one of those, given one of these filtered algebras, one does this straight construction called RYSZARD of this filtered algebra.
This is what Tomek talked about a week ago, RYSZARD,
something
right?
like this, right? So let's do it again, just one slide or so. So we look at product over n of dn times t to the power n. So formal power series of these differential operators with respect to t, but with some with restriction to the degree. Now the principal map is isomorphism to polynomials in cotangent bundle, right? So And the product defines a product on this polynomial cotangent bundle. So you look at the product. So it's a product from cotangent bundle, lifts via isomorphism phi. Can I show it somehow? Can you see it?
Yeah, we can see a cursor. We can see a cursor.
Maybe I can do it better. Okay, you can see a cursor anyway, right?
Yeah.
So besides using this isomorphism, so we have a product, obvious product, just commutative product on polynomials. We can lift it. Sorry, we have product on RD, just convolution product on in this one. So it gets transformed into product on polynomials and cotangent bundle. So we get what's called star product on these polynomials. Since the filtration has vitiated graded just commutative algebra, this product is just standard product of functions plus some formal power series in Tn. Pn's will be just by differential expressions in F and G, and you check that the commutator with respect to this product is the lowest order term as Poisson bracket. So let's play with it a bit better. So we use this isomorphism from differential operators to polynomials. Now what we can do is we can kind of start inverting things. So localizing our expressions, our operators dm, with respect to things which are invertible, which have locally invertible principal symbol. Right, so we just use the same product, but it extends on all smooth functions on cotangent bundle. So we localize this product to just all these expressions of this type. So we start with polynomials, right? So polynomials are ones which are homogeneous with positive k, like g equals 0k. But then we just use the formulas and extend it to other polynomials or other homogeneous functions for arbitrary k, both positive and negative. And localize, we just take a polynomial, one with respect to xi, and invert it where it's non-zero. And the product, well, it's still well defined. So the star product from above is still well defined, and produces an algebra of symbols of what we call subdivisional operators. Now remember that we had this inverse map, right? So map from polynomials to operators, differential operators. Well, this map, well, the inverse of this map extends to our symbols. So we can construct the map from smooth functions, sorry, it's stupid, this one. I was here, right? So we can use this map to construct a map from smooth functions. Well, modulo smoothing operators. This modulo smoothing operators is because we allow arbitrary negative powers. So we get this quantization map and just lift it to maps from C infinity to C infinity. So given n of those symbols, we just define, we can construct an operator mapping C infinity to C infinity. That's what's called, well, let's do it here. So let's call this quantization map. So given the algebra of smooth functions, we take something which has this kind of formal expression, formal expansion in homogeneous powers in xi, and quantization will produce an operator from S infinity to S infinity. It's a bijective modulo smoothing operators on both sides. Sorry, modulo smoothing operators, but we can lift it to everything. Now, these S, so these symbols S have to satisfy some estimates. Well, they have some estimates because they come from localizing polynomial functions on cotangent bundle. So these are these symbol estimates. It's not important at the moment. But what's important that they satisfy certain properties. So this quantization map has certain properties. First of all, if we take symbols of degree 0, so let me go back here. So 0 means that in this expansion here, there are only terms with k smaller equal 0. So these functions are bounded at infinity. So if you take operators for the 0, they extend to bounded operators in our sense. If you take symbols of degree -1, they extend by continuity to compact operators on L2. Intersection of the ON of these operators just gives smoothing operators, so that one. Now, if we take just union, so this union of these operators, well, we get some algebra of operators which actually has a smooth common domain of analytic vectors. Like for differential operators before, now all these differential operators have smooth common domain of analytic vectors, so calculus is easy to do. It's easy to compute with those operators. For example, it's obvious what's the sum of such operators. Now, moreover, if symbol is invertible as a symbol, so we know this algebra of symbols, then we call it elliptic, and then corresponding operator is Fredholm. That's a corollary of this statement. So invertible modulo compact operators. Moreover, they have this hyperellipticity property. So if symbol is elliptic, then if image of if phi gets mapped to a smooth function, then phi has to automatically to be a smooth function. So it's not just that they don't produce, they map smooth functions to smooth functions. So they do not, so we have this property, right? So they sit here. So they map smooth functions to smooth functions. So in general, they do not introduce singularities. But moreover, the elliptic ones, for elliptic ones, it goes the other way. If image is smooth, that function automatically is smooth. That's called hyperellipticity. And that's basically it. So given these properties, you just do the calculus, right? So if you want, for example, if you want to find resolvent, well, you take, let's say you have something of degree 0, takes its principal symbol, takes its inverse, write down the corresponding operator, and the corresponding operator will be inverse modulo things of the degree -1. So then you do the correction of degree -1, and you get inverse modulo something of degree -2, and so on. So you just use this calculus to construct inverses. So you get full calculus of these operators. Well, they are very useful, as we know, but let's go to the boundary. And I think it's a good idea to try to start with stupid examples. So the test case, the easiest test case of manifold of boundary is just an interval. Okay, so we look at the interval 0, 1. We look at the same operator, the only operator you can ever think of. It's id by dx. So it moves well. It maps smooth functions vanishing at both ends to smooth functions vanishing at both ends. Well, it does not generate a one-parameter group of diffeomorphisms, right? Even it's a vector field, constant vector field, we have a problem because the corresponding one-parameter group of diffeomorphisms would be translation. And well, we cannot translate from interval 0, 1 to anywhere. For example, if it's positive parameter, the 1 here will get outside the interval, right? So there is no group of diffeomorphisms. Well, we still want to be able somehow to work with this. So we want exponential of this operator. So we want to be able to work with it as self-adjoint operator. So in some self-adjoint closure. So there is this fear of Neumann about constructing self-adjoint extensions. And in this case, it's simple. So you impose boundary conditions. So you look at extend the domain, this operator, to somewhat larger domain. So you look at smooth functions which satisfy this boundary condition. So value of 1 is alpha times value at 0. Alpha is number of absolute value 1. Then D from exact maps C alpha to C alpha still. Locally, it's a translation in the interval, but actually extends to global action of R on this domain. Actually, the only thing that happens is that we take our interval 0, 1, and we glue the two ends. So we identify 0 and 1, but up to multiplication by this number alpha. So we have kind of we have a trivial, we have kind of non-trivial line bandu over the circle. Well, kind of, because overline bandus are trivial, but kind of non-trivial because we write it non-trivially, where at the gluing point we multiply by alpha, and then Rx by rotation, like before. So now we have a one-parameter group of automorphisms. So now we have a self-adjoint operator, and that's a self-adjoint extension. This is this, and according to von Neumann, this is a unique self-adjoint, has unique self-adjoint extension. For every alpha with absolute value 1, we get another self-adjoint extension. All of them are of this form. There are 2 comments. So boundary conditions, non-local. That's obviously non-local on the boundary, very much. Completions are geometric, right? So we do something, we identify boundaries, let's move functions by some sections of some bundle, flat band with flat connection. We need flat connection to leave differential operators to sections of this bundle. But still, we can't construct operators except the boundary conditions not local. Well, let's try another example, which is kind of more serious. Now, instead of interval, let's take half line. Okay, from 0 to infinity. Still the same operator. We start with, well, basically the same domain, except, say, we take Schwarz function. We have, since R plus unbounded, we have to see what we do at infinity. So we take Schwarz functions, which are infinitely differentiable with 0. And vanish at 0. I forgot to say that. Well, we take this operator. It's still X maps Schwarz functions. Well, it has no self-adjoint extensions. So general theory says that it has no self-adjoint extensions, and the way you look at it, so you look at the operator d minus I divided by d plus I inverse.
Sorry, RYSZARD, there is a question. Ali, please ask your question.
Please.
My apology for interrupting your talk. Is it obvious really that the C alpha in the previous example, is it obvious that C alpha is invariant under the differential operator in the previous example?
You mean, wait a minute.
Just
Let
one
me get
page,
to it.
please.
Yeah.
We define C alpha, all smooth functions.
Yes.
Yes. Is it obvious D maps C alpha to C alpha? For example, consider alpha equal to 0. This consists of all smooth functions which vanish at 1. But what is the reason that the derivative of every function with this property satisfies this equation?
No, it's not. No. Remember, alpha is absolute value 1. It's never 0.
Yeah.
Right?
Yes.
Right now. So think of it this way. What I'm doing is I'm taking this open interval, I'm closing it, so I've got a circle, and I'm choosing a flat line bundle over it. So functions C alpha are just sections of a flat line bundle over the circle. And the bundle, this line bundle is flat. This means that my differential operators act on it. That there's this flat, I've got this flat connection, which takes my differential operator and makes out of it the operator of the sections of this flat line bundle. That's the construction.
Yes, I see.
Okay,
thank you. Yes, welcome. Thank you.
Any questions? Welcome. Actually, it's not a trivial question.
Yeah.
Okay, let's look this one. Now we go.
I have a question.
Go ahead.
Could we start from the beginning instead of thinking the functions on M? Could we start with sections of line bundles?
Sure, it doesn't matter.
Yeah. So this would
no, it doesn't matter. It's what's the word?
Yeah.
I'm
And then
doing
the
fixes.
boundary value would be meant in the sense of sections of line bundles, and everything could be geometric.
Sure. No, you take a line, well, it's interval, you take some band, which would be trivial band, of course. And then you glue by some unitary, right? And or something invertible, let's say something unitary. And but it's the same. It will be isomorphic to this case, just with some multiplicity.
Yes.
So it's the overextensions here are trivial.
Thank you.
Okay, so now let's go the half line, right? That's kind of a more curious case. So we take these Schwartz functions, we take differentiation. So I did the same thing. Well, in this case, there are no silver-joint extensions. So Neumann theory says we look at this S, d minus I times d plus I inverse. This maps a range of d plus I to range of d minus I. Because d is symmetric, this is isometric from here to here, and then we extend it maximally. So the theory says that if we can extend it to a unitary, then the extension gives a silver-joint extension. If we can't, so if it extends to proper isometry or coisometry, then no, there is no silver-joint extension. In this case, this extends, it's densely defined, and is proper isometry with one-dimensional co-kernel. So E minus X is not in the closure of range of this one. It's densely defined, so it's and the range codimension of the range one-dimensional. So S becomes a proper isometry. So no boundary conditions will produce a divergent extension. There is no geometric completion at the boundary. So we have a boundary point 0. Sorry. Question or?
No.
No, go ahead.
Okay. Well, still, I want to complete this half line, so I have to do something with this boundary. I'm not unhappy about unbounded, about R, differential operators on R. What I'm happy about is that I have this boundary point where the translation breaks down. So I have to do something, and the only thing you can do is just add this isometry as an extra operator to your calculus. So we get, what do we get? We have these Schwartz functions. Remember, what I'm taking, somehow I want functions of d by dx. So I get Schwartz functions plus this isometry, but that's the same as looking at the algebra generated by this isometry. That's basically Teplitz algebra. Actually, it's a smooth version of Teplitz algebra. So it's called the Wiener-Hopf algebra. It contains smoothing operators in there, and quotient are Schwartz function are plus with 1-point compactification at infinity. So what we are doing is we are not doing anything with geometric. Instead, at 0, we add this algebra. Okay, so somehow it's not so bad because we know that Teplitz algebra, the unital Teplitz algebra, that's homotopic to constants. So it still behaves like a point, but kind of non-commutative point. So a completion in this case is non-commutative completion. We replace this point by d. Once we do that, we can we can compute S, and we can do such things. So we can do calculus.
Sorry, Ryszard, can you remind me what this tilde stands for?
Add 1. Add unit is utilization.
Okay, that's what I thought.
So basically, you take R plus and you complete. You add point at infinity. But it's point at infinity, right? So the functions which vanish rapidly at infinity.
Mm-hmm. Mm-hmm.
So basically, you take interval from 0 to 1, and you take functions which vanish with all derivatives at 1. Mm-hmm. Think of it this way.
Yes, yes.
Okay, so okay, we now continue. We do the same thing as before, right? We look at differential operators with this completion at the boundary, and then start inverting things as before. So you pick up again. We still have a degree, so we still have this degree filtration. We can do the same things. And actually, what really happens in this case is that at the boundary, we have a boundary, which is the standard operators, and then we have boundary kind of parameterizes our example. But before I do this one, there's one more statement or one more observation that we have to think about a bit. So the main property of series operators was that they map C infinity to C infinity. So they do not introduce singularities, so they are called pseudo-local. So now I want the same thing in the R plus case, and that's not quite automatic. So let's see what happens. Example, right? Again, example R plus, we look at our L2 of R plus, we pick up a basis of this form, where Ln are called Laguerre polynomials. Mark will recognize them. And then any Schwarz function has an expansion in terms of its ENs with rapidly decreasing coefficients. That's why they are useful. So they give isomorphism from Schwarz functions to rapidly decreasing sequences. Now, take a pseudo operators as before some symbol. Okay. So we use the same formulas as we did before, use the same quantization as before, and we try to act on these functions. Except that this time, everything is supported in R plus. So how does such an operator...
There is a question. There is a question.
Yes, could you please clarify what does it mean for a sequence to be rapidly decreasing?
Decrease faster than any polynomial.
Any polynomial. Okay, thank you.
So if we just take some zero-based symbol, then it's one-dimensional case. That's actually the formula. So you take a function, takes its Fourier transform, multiply by symbol. Okay, so that's what I'm doing, right? So I take function, Fourier transform, then I can't get the rest one. Multiply by symbol and take inverse Fourier transform. So I wrote the formula down here. It's the same formula, right? So integrate of xi. Since our ENs are rapidly decreasing, we can we can write them down. It's kind of easy to write down Fourier transform of these ENs. Right, so the way it works, Fourier transform of E minus x, remember that we sit on x larger equals 0. So Fourier transform will be rather not Fourier transform of E minus x has no bounded Fourier transform, but will be basically the Cauchy kernel. And then Ln will get, and the Fourier transform becomes a differential operator, as usual. So what we do is take this Ln, act here, and multiply and take by sigma and take inverse. Now, for this here to be a smooth function on x, then remember, so smooth function, if I've got smooth function supported in x larger equals 0, Wiener theorem says that has, well, depending on my Fourier transform, holomorphic extension to negative half space, imaginary negative imaginary half space. So for this to be a smooth function on x larger equals 0, this part has to need holomorphic extension to imaginary part of xi smaller than 0. Well, sorry.
I have a question, may I? May I have a question?
Sure.
About this extension. Why it is enough to check this existence of this extension only for x equal to 0?
Well, for no, it's extension for x larger equals 0. All of it, except so you have, so think this way.
No. In the line below, you have a symbol.
No,
at x equal to
for
0.
x away, no. So for x is larger than 0, this is automatically smooth. For x away from 0, this is automatically smooth.
Thank
There's
you.
nothing happening. Remember, this is some, I'm doing
Understand.
some nice smooth function, taking Fourier transform
Yes.
of something rapidly decreasing. There's no problem. The only problem is that x equals 0.
Okay, thank you.
Okay.
Mhm.
So for x is 0, this has a holomorphic extension. So for this to be smooth for OX, what you need to know that the corresponding expression here for OX is has a holomorphic extension for OX. Now we just want to set for x larger equal 0. We know that for x strictly different from 0, we are fine. Our problem is at 0. So that's the condition. This has to have a holomorphic extension. Of course, that's a very strong restriction. If sigma is polynomial, no problem, but it has to be kind of strictly homogeneous function xi. So, for example, absolute value of xi does not work. So we have to assume for these our pseudo-differential operators to work, so these symbols to define pseudo-differential operators which map smooth functions on R plus to smooth functions on R plus, so for them to be pseudo-local, well, they have to have this transmission property. So basically, it's a version of saying that symbol is polynomial is strictly homogeneous at x equals 0. I won't say precisely what it is, but in general, it's called transmission property. So it's this class of symbols with transmission property. So now general version of the same statement, right? So we take any compact manifold with boundary, take its opposite M bar, glue them together. Now I've got a manifold M union M bar. This is compact manifold without boundary, this one. And let's take chi to be characteristic function of M as a subspace, a subset of M tilde. Now, what are the pseudo-local operators? So now what we want are pseudo-differential, pseudo-local operators on M, which are actually restrictions of pseudo-differential operators on M tilde. Okay, so we look at operators of the form chi, p chi, where remember chi was this characteristic function, and p is just a pseudo-differential operator on M tilde, just our old pseudo-differential operator on manifold without boundary. So the ones that have this property that is cut down, map smooth functions to smooth functions, are called the ones with transmission property. So point number one, first of all, this condition only depends on the restriction of a symbol to cotangent bound of a boundary. I'm sorry, not M, but cotangent bound of a boundary. They have to have integral degree. So there's this homogeneity property, and our homogeneity property, so we have this, oops, no, not this one. We have this homogeneity property here of sigma here, this one. So this just extends to, has another form of homogeneity property. And so people seem to say that the symbols have transmission properties. So this one, if they such symbols, if they satisfy this homogeneity property, well, it's a theorem of Group and Hermander that this is actually equivalent to operators to be pseudo-local. So these cut down operators to be pseudo-local.
Ryszard, may I ask you a completely stupid question? I want to understand this opposite. So imagine M is just the unit disk. So then what is M tilde?
Another unit, oh, the M tilde is just a two-sphere.
Okay, so this is what I thought. Okay.
Opposite is opposite orientation.
Okay, thank you. This is what I wanted to do. Yes.
Right?
This is how we got our mirror quantum spheres, exactly like this.
Yeah, yeah. So, okay, so let's continue. Well, let's see. We have these pseudo-differential operators of this form with transmission property, right? So, basic observation is they are not closed under product. So, actually, there is a defect. If I take product up to such, remember chi squares chi. It's not the same as chi, pq, chi. The difference is something, and this is something. So this something's moving in the interior. That comes from a transmission property. And actually, they generate an algebra. It's called the algebra of singular Green operators. Okay, so point is that they are smoothing, so you just observe that they are smoothing in the interior of M. And remember, for pseudo-differential operators, the smoothing ones were, we worked modulo smoothing ones usually. So they were somehow not important for the calculus, did not show up in the calculus. So,
A question.
yes.
Is it true that L is a Hochschild coscycle? Co-coscycle?
No, it's not two-coscycle.
Probably not.
It's a boundary map, right? It's a boundary of map, Hochschild boundary of map. P goes to P chi P.
Ah, so it's a trivial.
No, not even then. No, not even then. No, no, it's just no. Not far from that, but no, it's not.
Mm-hmm.
It's the defect of the commutator of P and Q, right? Actually, you would rather look at the chi times P commutator chi and take boundary of that one. Hochschild boundary of this map. P goes to chi times P commutator chi.
Mm-hmm.
And take boundary of this one, right?
Okay.
So,
okay.
But well, so what do they have? They are smoothing in the interior, and you should think of them as some kind of pseudo-differential along the boundary, smoothing in transverse direction. Well, with smoothing in transverse direction, they could be also differential operators in the normal direction, right? But finite order differential operators. But this will be just differential operators in normal direction, no pseudo differential operators or anything. So that's our algebra. Well, our algebra, if we start with these pseudo differential operators and start to make an algebra out of them, we have to include those. So we have to include these singular Green operators. So we do that. And we get, we get what's called algebra of Green operators. So they have pseudo-differential operators. So these are from P chi, P chi. There are these kind of boundary contributions, which are called singular Green operators. Well, it's an algebra of operators on manifold on the boundary. So we also, these things here only act in the interior. So we add pseudo-differential operators on the boundary. We add things going from the boundary to the interior. That's called Poisson operator. We get things going from the interior to the boundary. That's called trace type operators. And altogether, we get this algebra of operators on, say, smooth functions on M plus smooth functions on boundary. We are not going to play with those because this whole algebra here, this go 2 by 2 it's funny. Okay, 2 by 2 matrices. It's isomorphic actually to the algebra operators to just this algebra B. So there is a theorem about Boutet de Monvel. Actually, we'll see at one moment where it comes from, which really says that the full algebra actually can be conjugated. So full algebra X here, it can be conjugated. Okay, again, just to algebra of operators on C infinity of M. There is this operator from T. So P is pseudo-differential, T is trace class, trace operator. It takes smooth functions, maps them to direct sum, and that's invertible. So if we conjugate by that, we can replace full algebra just by those. So we just work with those.
May I have a question?
Sure.
What can be said about the inverse of this column PT?
Well, just write down there's the inverse of it. It's actually, it's in some, you should think of, yeah, you think of with PT as Teplitz operator and inverse as a joint of Teplitz operator.
Okay.
Actually. So Teplitz operator along boundary. But you should think of it this way, basically.
Okay, thank you.
Okay, so this algebra D. So what properties does it have? As before, it's operators. Has the degree filtration. And filtration, so product of degree, one of degree n, one of degree m is of degree n plus m. There is no commutator property because of this smoothing operators because of these boundary contributions which do not commute. The symbols do not commute. But anyway.
And why did you change notation from k infinity to k?
Because I was lazy.
Okay.
I didn't think. Okay, no other reason whatsoever. Just
okay.
Smoothing operators. It contains smoothing operators. Now, if we pick up some coordinate which is transversal to the boundary, just pick up some color of the boundary, pick up coordinate such that boundary is given by xn equals 0, and manifold is given with xn larger equals 0. Then the singular operators, they have this type. They have actually unique decomposition of this type, where k is some seduction operator on the boundary with coefficients moving in the normal direction. These phi k such as some seduction operators. Sorry. Yeah, this moving. These phi k's are seduction operators on the boundary with values smooth functions, right? Not smoothing, but smooth functions. And I don't know what I did. Oh yeah, yeah. So, and then the way it works, if we forget the boundary, so what we have is a smooth operators in the on R plus, and we have finite sum of the form. Take a function, take its k derivative, evaluated boundary, and multiply by a smooth function. So if we forget boundary with boundary becomes 1 point, then it's kind of obvious what's here. And the only difference is that now we have in that boundary direction, we have pseudo-differential operators. So k minus 1 is called the type. Okay. It's not my name. Now, what about this algebra? First of all, it contains moving operators, and actually it's a minimal ideal in B. It's rather straightforward. These green operators, singular green operators, is also ideal in B. Remember, these are smoothing in the interior, and it is actually the maximal ideal in B. So the algebra B has two ideals: minimal K and maximal G. We'll use it later.
Okay. Sorry, can you describe? Oh, you are already describing. Okay.
Can I describe?
No, it's about simple algebra. What about the quotients by these ideals? Before
Yeah, that's what we are doing now, right?
Sorry? No,
that's what we are doing.
About the symbol algebra, okay?
So quotients, right? So full symbol algebra, we divide out by smoothing operators, and has two components. S are these pseudo-differential operators, modulo smoothing operators. So this is a space of symbols of pseudo-differential operators. But remember, they have to have transmission property.
Yeah, but what about the quotient B mod G?
We get there.
Okay, thank you.
Okay, easily, right? Well, B mod G are just, it's pseudo-differential symbols of transmission property, right? Now, the other component are these singular green operators. Those modulo smoothing operators, they have an expansion of this form. So it's kind of, so first of all, it contains singular green operators as ideal. Then we get T0, and the quotient is smooth functions on the boundary with values Schwartz functions in the interior direction. So that's complete information. Oh God, what did I do? Okay, that's complete information about symbols. So we have this B mod K. It's symbols of transversion property plus T0, and T0 is some kind of Teplitz-like extension, but careful of smooth function on the boundary. With smooth function, there's no cotangent bundle of the boundary, just the boundary, or no cosphere of the boundary, just the boundary. And quotient is symbols of G mod G, where G are these singular clean operators, modulo smoothing operators. Now this G has a grading.
Sorry, I have a question. What is the intersection of S and T0? Is it 0? In the first,
Yeah, that's 0. No, S and T0 is 0.
Okay, it's a direct sum.
No, it's not direct sum. They don't commute.
Not a product in the sense of algebras, but as
No.
basis?
Direct sum, yes, but they don't commute.
Okay.
Yeah.
Actually, I should be careful. It's modulo. Yeah, it is just direct sum. As the spaces. Good. So these symbols. So G, symbols of singular clean operators, also has grading, and the grading is given as follows. So I think I want something of degree star. What you get is you look at, remember, these symbols were set of differential operators on the boundary times normal derivatives restricted to the boundary. So star is sum of the degree of this boundary operator plus the number of normal derivatives. So somehow total degree should be the one what you expect, except that in the interior direction, you just have sort of differential things. In the normal direction, you have differential operators. So what I was saying is that these phi k are symbols, set of differential symbols on the boundary with values, smoothing operators on R plus. So on xn large equals 0. And as said before, T0 is again Teplitz type extension, so this T0 here, generated by dn and dn star. So point here is that this Teplitz algebra, we already noticed, it's not just the problem that there's no self-adjoint extension. Also, the result is that I can write down closed operator T, then I take dn, then I take its adjoint dn star, and they are different, but difference is actually in this case, well, actually it's of rank 1. So difference is a compact operator.
May I ask a question? About these smoothing operators in this direction perpendicular to the boundary. Does this K of R plus depend on, for instance, the tubular neighborhood of the boundary or the subpolar, or
it doesn't. No.
It's independent of the choice of the splitting.
No.
Okay, good. Very good. Thank you.
Of course, the expression depends, right? So the expression here depends on the choice of splitting.
Yes.
But these statements do not. They are moving in the interior, right? In the normal, they are moving in normal direction, right? So somehow, whichever choice you choose.
Metric.
No, it's whatever you choose, the result is the same.
Thank you.
Good. So now the subject of this talk, right? So actually, what we're interested in was what's happening with automorphisms of these algebras of the operators. And there's this classical result, this classical says that whenever you have an order preserving isomorphism from social operators to social operators, from M to N, then it's implemented by conjugation by a Fourier integral operator. Well, I wrote it up here. So there is a Fourier integral operator. Okay, I'm not going to explain how you construct them. I will say just a few words about them. But there is this Fourier integral operator such that alpha is implemented by commutator. You can formulate it differently. You can think about singly generated bimodules with respect to these two algebras. And statement is that singly generated bimodule, so singly generated free bimodule, is actually, or rather defines an operator from smooth functions on M to smooth functions on M. So just singly generated free bimodule of respect to psi infinity M tensor psi infinity M, and gives you an operator. And these are actually the Fourier integral operators. But I will say a couple more words about it later. So it has a degree, and conjugation is given by something like this. So conjugation is conjugation. B is unique up to a scalar. And I did it for scalar values, social operators here, right? So my coefficients here are scalar. Well, there is a paper more or less recent where the proof is extended to endomorphisms with coefficients in some vector bundles. So these will be social operators on M with coefficients, say, in vector bundle to N coefficients in another vector bundle. And then you show that these vector bundles are, there is a map with these two vector bundles isomorphic, and the operators are implemented by conjugation with something, right? So there's such B. It's not really far from one result to the other. The proof is almost identical. Okay, so
Another question,
yeah.
Sorry. What about alpha tilde, which is not invertible? Are there some results about some correspondence?
Bimodules, singly generated bimodules. It's much, well, no, actually it is somewhat more complicated. You can give, you can define, Fourier integral operators do not have to be invertible, right? But there is you need some kind of micro local statement. So alpha does not have to be invertible, but there is something with its behavior micro locally. What that does that, right? So it somehow you look somehow at symbols of these operators, and you can and see what it does to the symbols micro locally. If you are careful, you can construct on an operator like here. Okay.
And then it will intertwine instead of conjugate.
Precisely. And that intertwines. Yeah.
Okay, thank you.
And that's actually what Boutet and Melrose do. They write down intertwining condition and check that this defines an operator. Okay. Now we want something similar for a situation with boundary, and we really want, we would like all the grid operators, but it doesn't matter. So we remember that the same as looking at the corner. So we start with an isomorphism, order preceding isomorphism from these Boutet and Monvel operators to Boutet and Monvel operators, and we ask, okay, are they implemented? By the way, if you ever heard about Piasecki-Shapiro boundary conditions, so local boundary conditions, that's here what they are. Any kind of local boundary conditions can be expressed in terms of this Boutet and Monvel calculus. Okay, just assume M equals N. It really doesn't change anything. So
I have a question related to this simplification. So how much of the geometry of this manifold is encoded in this algebra?
Geometry, like actually everything. You'll see in a minute.
Okay. Okay, thank you.
Actually, you should think of it as what's the word? So symbols, right? Start looking at principal symbols. At symbols. Remember the symbol algebra that gives you smooth functions on the interior. The symbol algebra gives you smooth functions on the boundary with value smoothing operators in the interior. So the symbol algebras give you both the interior and boundary. So it gives you all the information. Point is that conversely, all you need is this kind of information about the manifold. Okay, let's some time, right? Good. So let's see what happens. So I have this automorphism. Now, immediate statement without thinking, and since it's a NCG seminar, we know what it is. We know that automorphism of compact operators is implementable. So there's a small twist on it called Edelheit lemma, which was proved, I think, in the 40s. And its proof is, as far as I'm concerned, very complicated. It uses something with Birkhoff about structure of lattices, but we know how to do it. But it really says that there is continuous map from C infinity M to C infinity M, which implements alpha. So we have implementation, right? We have our V. So our alpha has to be implemented by V. Question really is, what is this V? How does it look like? So we have to analyze the structure. So let's do the steps, right? So, well, what can we say about V? What can the say?
Oh, sorry, I have a question. Could you come back one page? Could you? Yes. Why K is since it's a minimal ideal, it must be preserved by alpha.
It's unique.
There could be many minimal ideals.
It's a unique minimal ideal, I see.
Unique. Oh,
yeah, sure.
So unicity is important.
You know, compact operators, wherever they are, if they are in some algebra, it's the unique ideal.
Okay, it's unique.
You know that, right? Sure.
Thank you.
Good. So, okay, let's see. We have this automorphism. We assume it's compatible with the filtration. So it gives automorphism of algebra principal symbols. So, few things. First of all, I think, yeah. So we remember the symbols. So let's look at B0 modulo B minus 1, right? So B0 modulo B minus 1, these are what? These are transmission symbols of pseudo-differential operators with transmission property of degree 0. So these are just smooth functions on the cosphere bundle, as usual, except that there is this condition on the boundary, this transmission property, which says something about homogeneity instead. So this is this twist. Basically, it says that we identify north and south pole at the boundary. Plus, of course, this direct decomposition, direct sum, smooth functions on the boundary. Okay, and so our automorphism has to map this to itself. So it's really to see that it maps this cosphere bundle modulo is going at the boundary to itself. We can see more because if we look at the center, we look at G0 mod G minus 1. So these singular green operators, so these things smoothing in the interior of degree 0, modulo things of degree minus 1. Quotient of this thing are just smooth functions of the cosphere of a boundary. And so this thing is preserved. So our automorphism defines automorphism of this one. So maps C infinity of cosphere of a boundary to itself. So we have so automorphism defines homomorphism of a space to itself, boundary to boundary, and on top of it, it maps not just restriction of cosphere to the boundary modulo of its relation, but the whole cosphere on the boundary to itself. Okay, So in particular, it gives the homeomorphism of cosphere of a cosphere of a whole manifold. Moreover, because of this property, it must be so it's not immediate. So first of all, it defines homeomorphism of cosphere of M to itself, which maps cosphere of boundary to cosphere of a boundary. That's pretty obvious. Now you check that it because it's maps commutators to commutators, and if we remember, commutators of substitution operators started producing Poisson bracket, right? So so this preserves this Poisson bracket on cosphere boundary, which has contact structure. So we have a smooth map which maps smooth functions to smooth functions from here to itself, preserving contact structure. Then it's easy to see that since it maps boundary of M to itself, its restriction to, I should have said, to this one, to infinity of cosphere on the boundary, is lifted from the boundary itself. So as said, homeomorphism is immediate. Smoothness, you look at commutators with vector fields. And what did it do? Sorry. Okay. And this fact that you can lift things, that what's happening on the cospheres of the boundary is just lift of what's happening on the boundary itself, is a corollary of the fact that contact structure is preserved. So commutators. Okay. I wrote it up again, right? So we get all of it produces. So that's the statement that on the boundary you get lift of a map on the boundary. Now this has a corollary, right? So page down. But wait, before I do, yeah, I'll go back to that one again in a minute. The corollary is following. So we have a simple ectomorphism, C alpha. It extends to, contact transformation, C alpha. So this, remember, it acts on the cosphere of the boundary. In general, acts on things of the form Bn modulo Bn minus 1. So things which are n homogeneous or polyhomogeneous with fixed n. It's not quite obvious how to glue them together to have something acting on the cotangent bundle. Right? I have somehow to lift it to cotangent bundle. Well, there is a way of doing it. That's Zinger. So you pick up a order one invertible operator in your calculus. It exists, and you define for any function on T star M. I'm removing zero section because I also have negative functions. So they are not defined at zero, of course, right? And the way I will define it, so F composed with, for n, composed with C alpha. So you think of Fs as kind of, we know how to write down operators associated to F, right? These are functional cotangent bundles. So we have our operator construction. So what we do is take F, take this sigma lambda to principal sigma of lambda to power minus n, multiply by F. Now we have a 0 degree symbol composed with C alpha. It's still 0 degree. Write down the corresponding operator. Take multiply by lambda to the power n, and take principal symbol. So this is really mapped from functions on the cotangent bundle of M to cotangent bundle of M, which lifts the action C alpha on zero homogeneous functions.
I have a question.
Yeah.
Is there an explicit formula for this raising operator lambda?
Essentially, well, yes and no. Yes.
Mhm.
You can, yeah, I guess you can write explicit formula. You should ask Elmar how explicit, but yes, there is an explicit formula. But there is something about it that I need to say something about in a minute.
Sorry, Ryszard, just I need to check. In this displayed formula, what it is that you define? The right-hand side?
I define left-hand side. My original C alpha.
On functions.
Action of C alpha on functions.
Precisely, right?
Yeah.
Remember, my original C alpha only acts on zero homogeneous functions, on cosphere bandu. I want to extend it to all homogeneous functions, right? To all functions.
And what does it mean to have this cotangent, but with this extra symbol here, this M section?
I remove zero section, so functions which are not defined as zero.
Yeah, you said it. I'm sorry. Yes.
Right? Yeah.
Yeah.
Since we have negative homogeneous functions, I cannot have M. Right?
Yeah.
So I remove zero section. That's all. So it's just a way of just using this symbol raising, or whatever we call it, degree raising operator to extend it. So I will say something about it. So you check that this extension does not depend on choice of lambda, actually. You check that one. And we get lift in particular on the boundary of the cotangent bandu. We just have the lift of our original map on boundary of M. So it was here we had this map on boundary of M. Okay, so these things are all used content zero homogeneous functions, right? And now I have to want all the functions on the cotangent bandu. So now we have all of those. There is a statement. So okay, once I have this properties, so once I could extend with C alpha to something on T star MM with this property here, well, it's called, it is invertible elliptic. So symbol itself, C alpha, is invertible elliptic in the sense of Battisti, Fourier-Stern-Schroer. So it's in kind of elliptic Fourier integral operator for manifold with boundary, symbol of Fourier integral operator, and there exists actually Fredholm Fourier integral operator from sin infinity M to sin infinity M, well, which acts, what's the word? Which basically conjugates, not conjugate, but intertwines certain with Boutet and Monvel operators on M with themselves. The symbol is invertible. Operator is not invertible, so it's Fredholm, so it's invertible modulo smoothing operators, modulo compact operators, but it's elliptic, so it's invertible modulo smoothing operators. So we have to invert. I will want to invert it to get rid of this alpha.
Sorry, is this operator lift of C alpha unique in some class?
No.
It's not.
No. It's modulo. No, it's never. It's modulo, always modulo smoothing operators. Actually, this is worse than that. It's basically it has some degree, and this invertible unique modulo thing, so degree lower than 1.
But what about the index of this lift?
You can't say anything about index. Actually, that's the point. You can't say anything about index. So we'll have to get rid of the index somehow. Right? We want to invert to get something invertible. So we have to do something with the inverse, with the index. Okay, I'm not, so no, I don't think I'm going to the previous ones. Actually, it's a cute statement. Let me just make it, because people tend to say that. And It's there are no proofs, right? This is yeah. Let's do a statement like this. So that's just for compact manifold without boundary. It can do the same thing with boundary. So suppose you've got a pseudo differential operator with a strictly positive. So first order. So positively one homogeneous in cotangent direction with, for example, absolute value of psi, and its symbol is strictly positive at one point in cotangent somewhere, right? Point in X and point of psi. So symbol is strictly positive somewhere. Corollary, spectrum of the corresponding operators is unbounded from above. It's more precisely, you can choose, you can pick up a neighborhood of this point X where this thing holds, and then you can get a smooth sequence of smooth functions with support in here, such that Pfn scarf Fn goes to infinity, where the norms of those are modular norms of those.
May I have a question?
Yeah.
I'm a little bit confused by this statement, since anytime if you have an operator which is unbounded in the sense of Hilbert space operator and which is self-adjoint, then the spectrum necessarily would be
Yes.
unbounded.
No, I didn't say it's unbounded. I
But-
said it's self-adjoint first order.
I don't
Yes,
know. Yes.
but first order implies
I
unbound.
need to know that I need to know whether it's remember, order is filtration, not degree. I know that if it's 0th order, it's actually bounded, right? That's all I know.
Mhm.
Now
So-
I've got one of order 1.
So you're saying that being order 1 does not obviously, at least, implies unboundedness. Yes?
No,
Okay.
no. Actually, no,
Uh-huh.
right?
No,
Eh,
once you know that the spectrum is unbounded, your operator have to be unbounded. But
Well,
but
but what's the spectrum?
once the spectrum,
Symbol. It's symbol, it's not spectrum.
no, in this statement, you are saying that the spectrum of P is unbounded.
No, sigma P is the symbol. It's
No,
the
but
principal symbol.
But the line below,
Below.
you are
Supremo.
saying that the spectrum of P.
Then the spectrum, right? If symbol is, that's the
Yes.
statement. If the symbol is strictly positive somewhere, then spectrum is unbounded.
Yes, and once you
Then
know,
operator is unbounded.
yes, exactly. Once you know that the spectrum is
Sure.
unbounded,
Yeah.
then the operator is also unbounded. Okay.
Yeah.
Mhm. Okay, thank you.
Okay, I'm not going to give you a proof. I want to prove something else. I need something else that should be more familiar to you. Well, that was the question. This can have non-zero index, but we can correct it, right? So how? And that's kind of statement why boundary case is easier. But the point is as follows. So suppose I've got some vector bundle of a boundary M. Lift it to the cosphere bundle of a boundary. Okay. Then the claim is that you can find a singular green operator P on the manifold. So it's actually a project P star equals P on top of it of order 0, whose range is the range of a symbol of this operator. So I can find a singular green operator. Well, as such, it's degree 0. It has principal symbol, which is a function on the cosphere of a boundary. We value some finite, finite subspace of functions. And I'm claiming that I can find one such that my vector bundle of a boundary is equal to the image of a symbol. In other words, so these P's really give local elliptic boundary value problems. Statement is that you can find singular green operator whose principal symbol is a family of rank operators parameterized by points on the cosphere of a boundary. And we can make it stronger. We can just construct not just one P, but we can actually construct a family, approximate unit of these singular green operators. So approximate unit for G. So a sequence of singular green operators, which are independents, and range equals to space of sections for each n, space of sections of rank n, vector bundle of a boundary. And the way you do it is pretty straightforward. So choose a color, choose family of smooth functions supported on this interval, whose restrictions.
That's a quick question. What is color?
A open subset,
The tubular network.
diffeomorphic to product here.
Okay. Thank you.
And pick up a family of functions who's restricted to a 0.5 form orthonormal basis. We can think of them as functions on M. They are supported inside here, only dependent on the normal variable, right? And write down for any function G on smooth function, write down operator pk of G is you take G, multiply by, conjugate by of Fi. So this is a function product, is a function on the scalar. So it makes sense to integrate it over a normal variable. So integrate over normal variable, like here, and then multiply by Fi again and sum up over A, small equal K.
I have a question.
Yeah.
About this yellow frame.
Yeah.
Is this correcting of this non-zero index problem?
It will.
Okay,
It
but
will in a second.
does it depend only on K theory, or does it use something more operator theoretical?
I don't understand the question.
Okay, so is correcting this non-zero index a problem with which can be solved using only K theory, or you need something beyond?
No, for that I need only K theory. But the statement here, if you think carefully of what I wrote here, around here, actually, remember there was this Boutet and Monvel theorem, which said that there is a diffeomorphism from sin M to sin M direct sum sin boundary M. That's what you use. Think of it. Basically, what I'm doing is I'm constructing an operator of the form 1 plus something singular green, which is a coisometry. So it maps really smooth functions on M to smooth functions on M plus an extra copy of smooth functions on the boundary of M. Right.
So this looks like a matricinal trick, in a sense. Maybe thinking, yeah. So I wonder how much depends on K theory.
Okay, and I do not understand the question.
Okay.
I just write down. You write down this operator, right? I just wrote down these projections, right? Some with K theory will come up a bit later, but just write down the projections. Okay. That's all, right? Good.
Okay.
Now your question, right? So obviously, given this problem of non-zero index, I want to use something like this, like here, to correct the index. So let's do that. So first a statement, and I wrote down the proof because I couldn't find it anywhere in the literature. And when I asked people, nobody really could give me a reference. So the claim is that closed orientable manifold admits pseudo-differential operator for index 1. It's kind of, everybody kind of believes it or something, but nobody really wrote it up. Okay, the proof here depends. It's a, well, I'm attributing it to Atiyah, but that's because the main fact comes first from his result. So what do we do? By UTC, uniform coefficient, universal coefficient theorem, the map from K homology to maps from K theory to Z is surjective. So K theory of X is an abelian group. We look at homomorphism from K theory to Z, and this map from K homology is surjective. Now, Atiyah, there is this chain character from K theory, here, from this one. Well, from K theory is from rational K theory to cohomology is an isomorphism. Well, since manifold is compact orientable, Hn is non-zero, hence K theory, so Kn actually, has a non-torsion component. Okay? So that's our non-torsion component, and that's surjective, so pick up a K homology class whose pairing to this non-torsion component is equal 1. That's because of the surjectivity here. Okay, so now I've got an element in K homology. Well, K homology is given by pseudo-differential operators and some vector bundles. So, well, so this means that I've got some vector bundle and Fredholm operator, and if n is even, then this pairing d equal 1. It's just index of this operator, well, dv lifted to bundle v. So I've got this pseudo-differential operator. Actually, I can find a pseudo-differential operator, and that was the point. So I've got this pseudo-differential operator lifted to vector bundle, and the pairing is 1. If n is odd, we have a pseudo-differential operator. Pick up a smoothing version of this operator. So it's rather kind of smoothed out characteristic function from 0 to infinity of this operator. So if n is odd, this is actually self-adjoint. So this makes perfect sense. And then this pairing is done how? So I take this operator, class V, since its odd class is given by, some invertible matrix over X with values endomorphisms in V. So take this V, cut down by this projection, this smoothed out projection P, and just to get something, so this is defined only where D is defined, right? So add 1 minus P. Okay.
Sorry, how do you understand this PVP?
Well, it's a V, well, just P is a projection.
Yes.
On smooth functions with values vector, our vector bundle. V is a map from vector bundle to unitary, from basis to vector bundle. So we just maps sections to sections.
As a matrix, yes? You view
think of V as a matrix.
Okay, as a matrix,
right?
okay.
P is projection to subspace, V is a matrix.
That makes
P is
sense.
back projection to the same subspace.
Okay.
Okay, plus 1 minus P. And now we have an index, right? And now again, pairing of D and V is index of the operator, right? So it's index of this operator. So remember, we got this finite rank vector bundle and the operator, and either we had D lifted to this vector bundle, or we use this one. It's still P's projection onto vector bundle. So there always exists an operator with index 1. Okay, good. Given that one. So
I'm sorry, I have a question. Can I ask a little question?
Sure,
Yeah, go ahead.
Yes. According to the theorem you mentioned, every manifold admits a pseudo-differential operator of index 1. I'm curious
with
why
coefficients. With coefficients.
So I'm curious, what is a manifold, compact manifold, possibly of even dimension, which doesn't admit a differential operator, not pseudo-differential, a differential operator of index 1? Is it an explicit example?
I don't know, but I believe it's true. Yeah, no, I don't know. I don't know the example, but yes, but that's what's the word?
Sorry, by saying
Actually,
that you believe.
let me think a second. Wait.
My question was that what is an example of a manifold which doesn't admit a differential operator of index 1?
Yes. I understand your question, but my question was related to Richard's answer.
Yes.
Look at this one here.
Yes.
Right?
Yes.
It doesn't matter whether D is differential or not. The index is the index of this one, right?
Yes.
And that's never differential.
Yes, but this from
It
this.
doesn't mean so. I'm not proving that one, but
I'm sorry, I didn't understand how this formula answered my question.
no, it doesn't really. No, I don't think I can. I don't think I know the example.
But
Yes,
sorry, Richard, you have said that you believe that this is true. So by saying that, you mean that you believe that
I mean that if I work enough, I can find an example.
that it is always possible to find differential operator, or
No, but there's example of a manifold where there is no differential operator with index 1.
Okay, I see. Interesting question.
But I don't know. I don't know the example.
Okay.
that I believe something, and this does not mean that it's true, right?
Yes, I see. Thank you.
Welcome. I've got another, 15 minutes? Or am I already out of? No.
You have 2 minutes.
2 minutes. No, okay. Okay, so 2 minutes. So I'm using this embedding boundary, right? So basically, this tells me that. Let's go back here. Right, this tells me that I've got this vector that I can write down a kind of vector bundle of a boundary and a singular Green operator. And when singular Green operator, and I can look at those singular Green operators as operators on vector in the endomorphism of this vector bundle of a boundary. The result below says that I can always find a bundle of the M and the operator on sections of this bundle, which has index 1. So I can find one on the image of the singular Green operator. So all I need to do is to page down. All I need to do, so basically I get this operator G, which I constructed on the boundary, transport it to the manifold via a singular Green operator, add 1, and now I have something of any index I want. So I can use it to multiply this operator associated to C alpha to get something of index 0, hence there's invertible perturbation. Such that difference is smoothing. So now instead of our original V, we look at VC inverse, and So now we have a situation, we have automorphism of B, which, well, X is identity on principal symbols. So we got rid of this C. We multiply by VC inverse. And V does not do anything on principal symbols of pseudo-tensorial operators. So remember, this G was green operator, so it's moving in the interior. And so, well, you look at this multiply, so the things on, well, you look at the symbols of singular green operators, and it's implemented by conjugation by something B. Okay, it doesn't matter precisely what, I'm not going to, I don't have time to say much more. So basically the one more statement is that we have this, how shall we say that? So we know how the thing behaves in the interior. We have this invertible operator that we used to get rid of its behavior in the interior. Now we need to find out how it behaves at the boundary. And essentially, again, we use basically the same method. We just need the automorphism of algebra of singular green operators. Now, so I wrote something about the structure, but the automorphism of so the problem is I could say nothing. I would just say that an automorphism of algebra of singular green operators is inner, except that we have these differential normal differentiations. So one has to be careful. But you can still prove that an automorphism is inner, and actually not on, so it's implemented by some multiplier, but in general, this multiplier, remember, principal symbols of singular green operators, these were smooth functions of the cross-sphere bundle of the interior, but with values smoothing operators in the interior. So multipliers of this thing will be again smooth functions, but with values multipliers of smoothing operators. I want somehow to say that this T is actually not just multiplier of smoothing operators, but smoothing operators itself. So there is a construction. So there is a proof that this component, it has to be in the smoothing operator. And it's something called micro-localization, and I don't want to talk about it very much, but and then the last one, you do use K-theory, right? The last one is, in the last bit, you use K-theory to show that this T, so remember, so this T was, so we got it something in here, that's the action on the boundary. Action on the interior is trivial, so 1 plus T implements our automorphism. But then I have to show that T is not just here, but T is actually one of our symbols, so green symbols. Remember, these are principal symbols. The symbols were functions on the cross-sphere of a boundary, smooth functions with some homogeneity properties, some behavior with derivatives. These were not just smooth functions, these were symbols. So I have to show that T is a symbol. And I use again the fact that I have this partition of unity for singular green operators to show that T has actually to be a symbol itself. So that this one actually holds. Since I don't have more time, I will stop now.
Thank you very much. Okay, any further questions or comments?
Any more questions?
Yeah. Okay, thank you from Chile. Elmar, would you like to weigh in? No.
No, I'm fine.
Let him be.
Could you repeat?
Thank you.
Could you repeat your question?
Elmar, would you like to weigh in? I mean, do you have something to add
You want
to
to say something?
Presentation?
No, I think just the answer to the question about the operator is that on any odd-dimensional compact manifold, the index of every elliptic differential operator is 0.
Yeah.
Yes, yes, the index is 0. Because the last the last part of cohomology should be an even dimension, and when the manifold is odd dimension, so the last cohomology part is equal to 0.
No, actually, it's because that
You usually
no, it's before the elliptic operators are on even dimensional manifold. Sorry, an odd dimensional manifold. Your K-homology classes are self-adjoint operators. So if you've got a self-adjoint differential operator, its index is 0. Actually, if you have a self-adjoint operator, its index is 0. So K-homology classes are given by self-adjoint operators, right?
So it was the case that I restricted my question to even dimensional manifold, examples of differential operator on
yeah,
an
even dimensional manifold, I don't know. No, even I don't know.
No, yes.
No, I think no. For even dimensional manifold, no. I think it's there is no. The set of indices is given by twisted Dirac operators that generates the whole K-homology group. So no. So whatever you get, so you will find a twisted Dirac operator of index 1.
What is the operator? Could you please repeat?
Some the twisted Dirac operator twisted by some vector bundle.
Twisted Dirac operator.
So you take the Dirac operator, takes some vector bundle, and you get an operator on a spin bundle tensor with vector bundle. And then these things exhaust K-homology for even compact manifold. So any value you get will be obtained by one of those.
In the even dimension.
In the dimension. And my computation says that you get any number you want.
Yes, I see.
Okay, Ali, if you are happy, why don't we ask Adam to ask his question?
Yeah, in fact, I have two questions. One is related to the spectrum of this operator. So could you say something more about for example, could you read the dimension of the manifold from the spectrum of such operators? Like in the growth of the eigenvalue.
But from what? What do you mean
From
spectrum?
asymptotics of eigenvalues, for example.
Oh, no, you mean when you start with elliptic operator, no?
No,
I'm not trying. That's what you meant by your question. No, I can't tell you much. I certainly can't tell you more than you can. I can certainly tell you less than you can say for manifolds without boundary.
Okay.
Remember, you cannot hear the shape of a drum, right?
Okay, you can.
Gets worse.
You cannot hear everything, but maybe just a dimension or volume, something like that. In this case, with boundary.
In the case of a boundary, I think no. You actually no. Remember, you can take you have your singular green operators. So remember, you can construct any operator on any vector bundle of a boundary. You can lift it to operator, say elliptic operator, on your manifold. Okay, so
Get-Grop has
think a second.
Results on heat trace expansions for operators in Boutet Monvel's calc.
So how much do they say?
Yeah, I guess I'm not completely sure. You can There's a problem. There are no infinite trace expansions as you have for pseudo-differential operators on closed manifolds. You only get a few terms, but you see a little bit.
Okay, thank you. And I have one more question. Since your operators form some algebraic structure and consist, or this structure consists from unbounded operators, so I wonder whether this theory is somehow related to this notion of being affiliated with some C-star algebra.
Being what? Sorry.
Affiliated.
In the sense of Gromowicz, for example.
Yeah, I know what you mean. No, so think this way. So differential operator, just the derivative d by d theta on the circle is not affiliated with an. No, sorry. Yes, it is affiliated to what?
To some C-star algebra, probably.
Which is what?
Yeah, which one?
Continuous function, probably.
Well, it's not. It's not a no. If it's affiliated with continuous functions or with Fourier transform of continuous functions. So think of it this way. Affiliated really means that you have your operator and you take over affiliated with some sister algebra. This means that, say, C0 functions of your operator are in your sister algebra. Okay, you need self-adjoint operators, say, and C0 functions of your operator are supposed to be in your sister algebra, right?
So you need somehow to take a Fourier transform in order.
Yeah. So you have to be able to take continuous functions when you get infinity. Now, the problem is that things. So you can do it this way. Take so you can do, for example, take all these so somehow affiliated to some algebra is kind of very weak because so you take continuous functions of all things self-adjoint operators in that calculus, bounded self-adjoint operators. Continuous functions when you get infinity. You can in algebra. It does so. Remember, taking absolute value is not allowed. You cannot take square root of square of delta, for example. You cannot take absolute value of an operator, right? But in the calculus, but given an operator, you can take absolute value of the square. Right? You can take absolute value of it. So you take the algebra of operators, you take all functions, let's say vanish get infinity of self-adjoint elements, write down an algebra, you get a C-star algebra. And yes, of course, all these operators are, all these Boutet and Monvel operators are in the multipliers and the multiplier algebra are affiliated, but that's by definition. So kind of affiliation is I guess, a wrong term in some sense. Meaning affiliation, you have a C-star algebra and what's affiliated with the algebra are all the self-adjoint operators whose functions vanishing at infinity sit in the algebra. So it's if you'd be interested, you would have to be that's interesting the other way. So it's the way that you start with C-star algebra, and then there are some concrete operators that you would like to have affiliated to this algebra.
Yeah, I think I understand what Ryszard is saying, because you see, Voronowicz developed this theory of how to generate a sister algebra by affiliated operators. So if you are just saying, I have an unbounded operator and is it affiliated to something? Well, yes, it is. It's really interesting when it's given, you have a given sister algebra, and then you want to see if a certain operator is affiliated
operator.
to this relation. Okay, so that's why.
Yes, but I would say that there is some canonical choice of a sister algebra in this context. Just take continuous function on your manifold. Yes, so this is
No,
natural.
That's no.
It's too naive.
No, you don't. Of course, it's not.
Maybe on the cotangent bundle, the zero section removes. There's another natural candidate.
No, guys, not even that. Wait, Thomas, wait, Thomas. This is a non-commutative algebra.
Yeah.
It cannot be affiliated to some commutative algebra.
Yes. So I said there's another canonical choice. It would be the convolution algebra of the tangent groupoid.
Yeah, but these are social operators.
That's the
These are principal symbols of social operators, and no, pseudo-differential operators are not affiliated to that.
Okay, that solves the problem.
No, they are not, because if you have a non-commutative algebra, everything affiliated to it has to be commutative. Has to be commutative algebra. Basically, you look at C0 and C0 on some space, and you look at continuous functions on the same space.
Okay, I'm happy.
In commutative case, that's what affiliation means, right? That an operator is affiliated to an algebra if its continuous functions vanish at infinity, so that you have something bounded, sit in that algebra, by definition.
Mm-hmm.
You just want to have a calculus, use the calculus in your sister algebra in this class of affiliated operators. And where you can do it, because operators uniquely defined by functions, continuous functions, vanish at infinity of this operator. It's enough so that you can start finding out what's the sum, what's the product, and what's the product. But you have to be careful.
Happy, Adam?
Yes, I'm happy.
Happy. Okay.
Yes.
You seem puzzled, but
I had some problem with my internet connection.
okay.
But yes, I'm happy.
Okay, great. Anybody else?
Yeah, I have a question.
Okay.
I have a question about this correction of the index. At the end of the day, you want to kill the kernel and the cokernel to obtain an invertible operator. So I understand that you can kill the index, but I don't understand how are you killing the kernel and cokernel at the same time.
You add what's the word?
I missed this point.
No. Think of it. So you have an operator with kernel and cokernel same dimension.
Yeah.
And that's elliptic, so these are smooth functions, right?
Oh, yes.
So you pick up finite rank operator, which goes from kernel to cokernel, and just add to the operator. Right? It's everything is the same. Same modulus moving operators.
Yes.
There's finite dimensional.
Yeah. Okay.
Anybody else?
May I ask another question?
I said anybody else.
Okay. Maybe
it's okay, Thomas.
No, it's okay. Go ahead.
Okay. I have a question about this transmission property. So you are playing with this double of the manifold with the boundary.
Yeah.
What if instead of taking this double, we are composing cobordisms? Does this transmission property make sense in this context? And does it allow to construct some kinds of, I don't know, topological field theory? Because
no,
no.
So it does not depend. So to take double, it doesn't matter what you did. The only everything that happens is in the covariant boundary.
Yes, but you can have boundary consisting of two pieces.
Yeah.
Like, and then instead of gluing along the same boundary with using this identity map on the boundary, you can compose cobordisms. And then I'm asking about the possibility of formulating the transmission property for this composition of.
Hey, Thomas, what do you mean by composing cobordisms?
So you have two components of the boundary.
Yes.
And you are gluing consecutive factors of the cobordism, gluing with respect to only this one part of this boundary. Then you have a composition of cobordisms instead of the double.
No. So, yes, Thomas, no. So when you look at the operator, so the singularity part, this transmission property, it's so first of all, if you don't, I don't know what you're going to do in the other part of the boundary, the free floating part of the boundary.
So your computation is local with respect to boundary.
Computation is completely local. So this, the fact this basically the question is you want things which satisfy, which are pseudo-local. Okay, do not introduce boundaries, right?
But one of your examples, if you remember, there was an example of an interval.
Okay,
with
let's
some
go back
transition functions on the boundary. So it was not local.
Where are we? So
you had two components of the boundary. You had some gluing this alpha.
This one, right? Yeah.
Yes, for instance, yes. So it's non-local. This boundary.
No. But here you get things, right? Because basically what you are doing here is you are looking at your manifold with some was a flat bundle, and you are gluing those. So it's not just manifold you're looking at, you are looking really at manifold with local coefficients. But of course, when you start doing cobordisms, things happen.
So I'm confused. So
maybe it becomes
are these non-local examples here particular cases of your general case you are considering in your
but try again.
Or not?
No, these examples are not.
So this is a non-example.
This is a non-example.
Okay, thank you.
Maybe it becomes clearer if you say that the transmission property guarantees that functions that are smooth up to the boundary are mapped to functions that are smooth up to the boundary.
Yeah, I understand this.
And then it's really a property very local at the boundary. It's only in the interior. It's no condition. It's just at the boundary where
Yes. Yeah. So therefore, I asked about possibility of composing cobordisms instead of taking this double. But what is this double? This double, it is a cobordism between your double and an empty manifold. So it's a special case of a cobordism. It's like cancellation. It's a cancellation of cobordisms.
How do you get there, if I may ask? How do you get to any cobordism whatsoever here? It's not a cobordism.
It's not a cobordism.
Of what? Cobordism?
Cobordism
of what? Sorry, cobordism of what? You think of a manifold as a
closed manifold is a cobordism between what?
I'm just taking I'm taking manifold, building up another manifold, and I'm building up a closed manifold. That's all.
Yes.
What kind of cobordism is that supposed to? Sorry.
It's a closed manifold is a cobordism between empty and empty.
Thomas, what do you...
Yeah, but yeah, but I'm not building anything, right? I couldn't care less what's happening away from a boundary when I glue something here. Okay, Thomas, it's cobordism of which manifold? Cobordism of which manifold?
The double from empty to empty.
No, the double is just the double is just closed manifold. That's it.
Yes, and every closed manifold is a cobordism between empty to empty.
Sure, but now I've got a manifold M. What does that have to do with cobordism? Gluing the string on.
You are glue, yeah, but then you have this M and M bar, yeah. and composing them to this double, you are in a sense cancelling this manifold as a cobordism between something non-empty to something non-empty. You obtain cobordism from empty to empty.
I'm sorry, if I start with the M, what kind of cobordism is it?
Cobordism, okay, for M.
I start with M.
I think that Tom...
And the boundary... Stop, Adam.
M bar is the inverse of M, yes?
M is a cobordism from empty to the boundary of M. M bar is a cobordism from the boundary of M to empty. And composing them two, you obtain a cobordism from empty to empty.
Sure, but what does that have to do with
during constructing this double, you are constructing, in fact, a cobordism. So my question was
no, I'm adding, I'm taking cobordism and as you said, from boundary of M to empty, and I'm taking minus cobordism and summing them up. Then I could get 0. And I'm not constructing any cobordism. By definition, if I've got a manifold, that this manifold represents cobordism from its boundary to empty.
Yes.
And well, there's a group of cobordisms, right? So if I can take minus 1 and add them up, but I don't have to. I can add identity. Identity on the boundary, right? Just some color around identity. I can add this one. Same kind of computation, same kind of result.
Yes. So how it is related to the problem of transmission property and the composition of cobordisms, which was my question.
I'm not sure I understand your question. There's the cobordism, cobordism doesn't play any role here.
Okay, I have a suggestion, and maybe this is a discussion which requires Blackboard being together.
Okay,
yeah, that's true.
Getting out of hand. So now, really, anybody else? Go ahead, mine. Go ahead.
Thanks for the talk. So in the first slides, you showed some recap on strict deformation quantization.
Yeah, very
so
basically.
And so which is related to tangent groupoids, analytic index, and so on, so forth. Does your extended calculus to the boundary extend also these settings?
Yes, except you have to remember that somehow at the boundary you get a non-commutative. Even the 0 for the term is non-commutative. So there is this bit here at the boundary. It's actually, so these, at the boundary, these things, the symbols, these are actually functions on the, well, cos-phi of the boundary with values smoothing operators.
Mhm.
So these are non-commutative. It's
Okay.
not that much worse in the sense that it's kind of, could think of it as deformation of kind of deformation of Azumaya algebra. Okay, so in this sense, not much worse. But there is this non-commutativity here.
Can you relate this to some deformation groupoids? You know what I'm saying? Like an extension exact sequence that you get the classical case where you have psi 0 in the middle, functions on the tangents as the quotient.
Yeah, I know. But problem is so you get.
So you get some. Yeah, I'm not saying that
you can just see. You can just as well think of this here, right?
Yeah. Because
when of course transversal, there's nothing new happens. Transversal, you have standard. Think of star product transversal, right? And sorry, along the boundary. But so this is the best you can get, right? You get the septis algebra, you get this isometry, proper isometry. So you are deforming kind of functions with values in this extension.
Yeah.
Maybe one could
that's
add
the best,
Bouvet.
right? Sorry?
Bouvet and Candelis have constructed a sort of groupoid picture for Boutet and Monvel's calculus, but it's not quite, it's already an older result from maybe mid 2015, 2016, something like that.
Yes, and it's sort of, it's not really.
Not related.
It's not really, right? No, it's not quite.
Not quite.
No, it's not quite, yes.
No. And the problem is this one, right? So,
but it's an attempt, yeah.
True. Well, if you want, you should think of actually kind of Fedosov did something like this, but not really. Yes, you can think of deformation picture, right? Except that, so your group, you will see what's happening here with 0 here is that you get a tangential semi-group, right? Sorry. It's irritating. Where was it? Here. Actually, no, this next one. Right, so at the 0 here, right, you get tangential semi-group. So remember, this tangential groupoid is just the fact that you can take tangent band, we can integrate it to pseudo differential operators. That's all. Right, so tangential groupoid is just the fact that it's integrated to the pair groupoid. Okay, and here it's not. Here you get only half of the thing. Here only inside you have the translation in both directions. So inside you are fine with tangential groupoid.
Yeah.
But at the bound at the 0 point here, you have translations in one direction. So you can use that, and you can actually build some calculus with that one. But that's precisely what's happening here. You have to be, you get similar things. It's not really a groupoid in this sense, right?
Maybe
it's a semi-group, right?
Yeah. So maybe you get Toeplitz algebra generated by more isometries, or something like that.
You can have that one, yes, if it's a corner or something. Yeah.
Like the ones that show the different directions.
What do you mean, commuting isometries? Or?
I don't know. Maybe could be.
Don't know.
Yeah,
Could be up to moving things, right?
Yeah. Okay, I see. Thanks.
Okay. Anybody else going once? Anybody else going twice? Anybody else? And let's thank our speaker again.
Thank you.
Let me stop the recording.